Okay, everybody, time to move on to liquids. All right, we talked about our gases and we finished up with Dalton's law, and now we're going to move on to liquids. And kind of a blend between liquids and gases here, but we'll talk about some of the rules with liquids and vapor pressure. So, if we move on a little bit, we could talk about a liquid in general, and we could take a look at this picture. And what we find is that if you have a certain liquid, you have molecules in the liquid here, say it's molecule, this is attracted on all ends by some molecular forces, right? So if this is water, you would have a water molecule that would have hydrogen bonding in all different directions, 360 degrees around there. Then that would hold molecules of the liquid in their liquid state. However, if that little molecule finds its way to the surface, it would only be attracted from the sides and the bottom. It would not be attracted to the top because out here would be empty space. So what we find is if liquid molecules have enough kinetic energy, if the temperature is certain temperature and you have a certain amount of speed or kinetic energy, those molecules can actually pop off the surface and into the space above this. So you can see in the second diagram here, you'll have molecules of gas from the liquid that are bouncing around the container in this closed container. Now, molecules of a gas that are above a liquid here is called vapor. Okay. Now, again, this follows the same rules as any other gas, but we call it vapor because it's made of the same material that the liquid is made of, the solvent. So if this is your solvent down here, that solvent would have its own vapor. All right. So important to know. So the subject today is going to be liquids and something called vapor pressure because this vapor above this liquid produces pressure when these molecules hit the walls of the container. Okay, so a couple of terms we want to keep straight, and one of them is called evaporation, which you've heard before. And evaporation is simply the escape, okay, of molecules from the surface of a liquid, and the key is the surface. This is going to take place from the surface into the gas phase. Okay, this is going to occur at all temperatures. Okay, and if you want to increase this evaporation rate, there's a few things we can do, right? We can heat this liquid up. We'll get those molecules moving faster, and they'll evaporate faster. We've seen this before when things dry. Or you can increase the surface area of the surface. And as you expand that surface out, more molecules that have a better chance getting to the surface, and therefore a better chance of becoming vapor. And of course, if you have vapor, then you have vapor pressure at that temperature. Okay, of course, if you change the size of the surface, you would have to change the size of the flask. So really, the vapor pressure would not change. All right. Again, you're increasing the evaporation rate if you do that. All right, so what is really vapor pressure? Let's define it and then get into some of the things that we have to include here. Okay, number one, vapor pressure is the pressure exerted by a gas above its liquid. Okay, so you'll always have some type of vapor above this. Okay, and this is going to be dependent on a couple of things. Number one, it's going to be dependent on how hot the liquid is. Again, temperature is that average kinetic energy. Okay, and as you add heat to this liquid, you will have those particles move faster. More likely, they would become a gas. Okay, they would move faster, which would then cause more evaporation. Of course, increased evaporation and increase the vapor pressure. Okay. Another thing you want to keep in mind is the type of liquid. Okay, and the intermolecular forces then in the liquid, or the type of the liquid that you're dealing with. All right, so that's important to know that your intermolecular forces are going to be key in the liquid, because if you have very weak forces, so think about that. If your solvent molecules are very weak in the liquid phase, then more likely they're going to get out of the liquid phase into the vapor phase at a given temperature. All right, and that would probably that's going to produce more vapor pressure when you have weaker forces. And again, well, what kind of things have weaker forces? That would be nonpolar materials, which have London forces. So again, this is where you really want to think, right? You want to think, don't memorize here. You want to think about, what does it mean to have weaker forces in the liquid? Really transfers to a higher vapor pressure, because more likely you're going to get into the gas phase. And of course, this is going to increase when you increase the temperature. All right, some type of liquids that do this are hydrocarbons, anything with a CH in it. Okay, gasoline is a good example. Paint solvents, lighter alcohols are going to do this. Ethanol and methanol are simple alcohols. Hand sanitizer is a good example, where you'd put some on your hands, you rub your hands together, and then those would dry off very quickly because the molecules in the gel with a little bit of heat will separate. Okay, and if you have strong forces, you would have a lower vapor pressure. right? Because those molecules would be held very tightly in the liquid up here, less likely to come out from the surface, and because of them, you would have a lower vapor pressure. Okay, anything water-based, antifreeze would be a good example because that's water and alcohol. A concentrated aqueous solution, okay, where you have a solute plus a solvent. Again, a solute would attract to the solvent, right? Attract solvent, okay, and those attractions will help you keep the solvent in the solution more, so you would have a lower vapor pressure. So these kind of things you want to really think about. Okay, really important to know exactly what's going on. All right. So that's a good thing to think about. Again, and then in these, you're going to be independent of the quantity of the liquid, right? We don't care about how much liquid we have. What we're interested is in the temperature and the intermolecular forces. Just because you have a lot of liquid doesn't necessarily mean that you're going to have a greater pressure. So it's independent of that. All right. So what we want to do is, as we know, as you heat a liquid higher and higher and higher, okay, we eventually reach the point where that liquid boils. Okay, so at that point, you would then see bubbles being formed within the liquid itself. All right. Now you have to think about a couple of things here because this can be a little bit tricky. Is that you have two types of pressures. You have and if you look at diagram number 1 here, we'll see that not only do you have your vapor pressure of the liquid here, if you think about the vapor pressure of these arrows pointing up, but you also have you also have an atmospheric pressure that's also ever present, right? You always have the atmospheric pressure is always there. Now, if that's pushing on everything, what that does is that prevents a liquid from boiling because it's actually putting a strong weight down on that liquid. So if you heat this liquid and you produce more and more vapor, you get to a point where the vapor pressure pushing up of that liquid is going to counteract that external pressure of the pressure pushing down until they exactly match. And if they match, then you can start forming liquid bubbles in here and the liquid will boil. So the temperature at which the vapor pressure of a liquid, so I want you to think of that vapor pressure as a strength of that liquid to pushing away the atmosphere, equals the external pressure on the liquid, you then would have the temperature at which that liquid boils. Okay, so think of it as lifting the atmosphere off. Okay, I try to think of it as, a weightlifter, or if you've gone to the gym and you lift weights. If you want to lift the weight off the rack, or if you want to bench press something, if you want to raise a weight, or you want to curl a weight, you have to put enough energy in to surpass the weight of gravity, right? That weight is pulling down. You want to push that weight up or pull that weight towards you. You're going to only do that if you can counteract that weight. All right, so that's interesting to know. All right, so what we call the boiling point is when the vapor pressure, think about pushing up, is the same as the external pressure pushing down. All right, and if you get them exactly equal, you would then have something called the normal boiling point. Now, the normal boiling point is when that pressure pushing down is exactly 1 atm, or atmospheric pressure, and that's when water would boil at 100. Okay, so again, if the pressure pushing down is 100 and you're at 100 degrees Celsius, then the vapor pressure of water pushing up will also be 1 atm, or 101.3 kPa, same thing, and that would be called the normal boiling point. Now, let's just say we weren't at 1 atm and we went to Death Valley, California, which is below, sea level. Now you have a greater pressure pushing down. You can see by these heavy arrows, you have greater pressure pushing down. Okay, in order to boil, you have to have a greater pressure pushing up, right, to match that pressure. Just like if you were lifting a heavier weight, you'd have to simply push harder. Okay, the way we push harder on a liquid, the way the liquid pushes harder, is that you gave it more heat and you have more vapor. So your boiling point would need more heat to boil, okay, and you would actually have a higher boiling point at that point. So you might boil at, you might boil at 110 Celsius instead of boiling at 100, okay, because you have to push that much harder against the atmosphere. So if you think about it as weightlifting, it really makes things a little bit easier. All right. In contrast, if you went above sea level, okay, onto a mountain maybe, okay, up on a mountain, Mount Everest, okay, now notice the dotted lines, you're not pushing as hard. So think about it really lightweight. If you're trying to push a lightweight, a very lightweight, then you don't have to push that hard. If you tried to curl or push up a feather, you wouldn't have to push that hard. So because of that, now you would have a lower boiling point. Say maybe you'd be boiling at maybe a 70 degrees Celsius instead. All right, so you need less heat to boil, and now you would have a lower boiling point. All right, so again, in summary, boiling is really a pressure thing, not a temperature thing. The temperature simply is the arbitrary tool to get you to the vapor pressure needed to push away the atmosphere. Now, again, most of the time we're going to be over here, right? Most of the time we're going to be in a situation where we're at 1 atm. However, that can change based on the elevation. You might see this on a pasta box or on a rice box where it says adjust the cooking time for elevation. You would have to cook longer here, right? Because you have a cooler water. You have less heat here. And here you could cook shorter. Sometimes you can sometimes this is used called a pressure cooker. Pressure cookers cook under higher pressure and therefore hotter water, which decreases the cooking time and making sure meats and vegetables all get soft and good to eat. All right. So if you take a look at these two, let's just say you have liquid A and liquid B. Good way to think about them. They're both capped at the top. They both have some vapor pressure. You can see the liquid A has a more vapor surrounding its space. Liquid B has less vapor in its space. The key is they're both 1 atm, both at 1 atm pushing down. Okay, and they're both. This is external. Okay, and they both at 25 Celsius. So they're both the same conditions. The question is which liquid would have the highest boiling point. Explain. Okay, you would probably think that liquid B would have the highest boiling point. Okay. Okay, because liquid B would have the lowest VP. Okay, so it would not be pushing very hard. Okay, and therefore you would need more heat to boil it, so you'd have the higher BP. Okay, because you need more heat needed to raise it up to push away the atmosphere. How much this vapor in here would need to push off the atmosphere to boil. Okay, which liquid have the weakest intermolecular forces? I would probably say liquid A would have that because, again, you have more vapor compared to liquid B at the same temperature. So more molecules are escaping this, right? So you have more vapor at the same temperature. Okay, so you have weaker forces. Okay, weaker liquid forces. All right, and in 3, which liquid could possibly be water? Okay, if you looked at these two, I would think the lower vapor pressure, again, polar substance. So liquid B would probably be water. Okay, you have less VP, which would be stronger intermolecular forces. So that would probably most likely be water. And there's your hydrogen bonds. So again, you could look at this and compare liquids that well also. Again, hand sanitize, like we said before, you just have to rub your hands and it dries very quickly. It would be alcohol. All right. In reference table H is a vapor pressure thing. And again, this is what we'd find on the reference table in your reference table. Again, on the bottom is temperature in Celsius. On the side is vapor pressure in kPa of these 4 various liquids. Okay, a couple of things you want to be aware of is it goes by 5, 10, 15, 20, 25. It goes by 5s here, okay? However, understand it goes from 5s here, but this would be 10, 20, 30, 40, 50. It goes by 10s here. So just be careful about the scale on both sides. But again, temperature and kPa. Something significant about the dotted line in kPa, you guessed it, that is your standard pressure. All right, so your standard pressure on the curve is at that. Now, that's significant because if these vapor pressures of these liquids become the same as the standard pressure, you would then boil, right? So your boiling points, your normal boiling points for these 4 liquids are at these temperatures. Okay, those would be a normal boiling point at that point. So again, I like to use water as your reference. And again, where do you see that? That lines up exactly at 100 degrees. So at 100 degrees, the vapor pressure of this line, okay, is equal to the standard pressure, which is atmospheric pressure, okay, which is ATM pressure, and those liquids would boil at that point. All right. So again, when you're boiling, you got to know two pressures: the pressure pushing down, okay, and then also the pressure pushing up. All right. So if we take a look at these now, again, you notice these four liquids, they also spread out as you do this, right? So as you spread out, you'll see what's the reason for each gas having its own, each liquid having a different boiling point is, again, the type of liquid that it is and its intermolecular forces. So again, propanone, okay, is an interesting molecule. It's got, okay, a double bonded oxygen and two carbons on either side, fairly symmetrical. This is going to be fairly nonpolar. Nonpolar is going to have your weakest forces, and of course, it's going to have very high vapor pressures. You can see this jumps up pretty quickly compared to anything else at a temperature. So if you went to 50, you'd see the highest curve here would be propanone. Propanone would have a high vapor pressure compared to the other ones at the same temperature. So again, you'd have your weakest IMF, which give you your highest vapor pressure, and of course, your lowest boiling point. All right, again, really important that you know the relationships here. Okay, on the other end of the spectrum would be ethanoic acid. Again, ethanoic acid would be this guy, very, very polar, a very, very polar end to it. Okay, very asymmetrical. Okay, and again, asymmetrical is going to have very strong forces. Okay, so strong forces, again, would not produce a lot of vapor. And if you don't have a lot of vapor, you don't have a lot of push against the atmosphere. So you would really need to heat that liquid up higher, and you would, because look at the vapor pressure here. It would be 105, 110, 115. You're talking about, your vapor pressure of about like 117 Celsius here, which is a fairly high boiling point compared to water. All right. So really important. So basically, and again, if you wanted to take a look at this really quickly, again, ethanol, we looked at the structural formulas of those two. Again, we know the structural formula for water, very polar. Okay. Ethanol would have, an OH here. Remember your alcohols. Okay. Again, less polar, but a little less polar than water, but still somewhat polar, but not as a little bit more polar than propanol. Okay, so you can see these three. And again, this is table H. You will have access for this on the reference on the test. All right, if we go to this thing, just a couple of little ways to kind of like summarize this whole thing. Okay, so liquids with strong intermolecular forces would have weaker vapor pressures and therefore higher normal boiling points. Again, more energy is going to be needed to break these intermolecular forces and turn them into a gas. Sorry about the bell there. Okay, so in this case, because of that, you would have this situation. Okay, because of attraction to the solvent, the addition of a solute. Okay, so again, this is from the solutions unit. Because of the attraction to the solvent, the addition of the solute decreases the vapor pressure. I mean, more attractions. Okay, and what we'll do is it will increase the boiling point. We know that the boiling point increases when you add solute, and the freezing point decreases. Okay, vapor pressure is going to always increase with increasing temperature. Okay, and a liquid's boiling point is the point at which the vapor pressure equals the external pressure. So it's pressure equaling pressure. So the VP pushing up must equal the external pressure pushing down. And when they exactly equal, then the liquid would boil. Okay, so using table H, we can get an idea of how to do this. So if you use table H along with this, let's just say you looked up propanone on table H, okay, and you were playing around with propanone, all right, and you had 50 kPa, and the atmospheric pressure was also 50 kPa. That means one was pushing up and pushing down at the same. That means the liquid would be boiling. If you look up that on the chart and you look up your boiling point, I get about 37 Celsius. Okay. The last column here is simply looking at these based on the weakest intermolecular forces of 1 to strong. Okay, we can say 1, 3, 2, and 4 based on the thing here. Okay, if you look at this the other way around, if you look at your boiling point on the chart and you look up propanone, you would see you'd probably hit a vapor pressure of 155 kPa. And if you had 155 pushing down and you're boiling at 70, then the atmospheric pressure would also have to be 1 kPa. So a little pattern here, you'll see that these two columns would always have to be the same. If water was boiling at 50 Celsius, okay, and you check the vapor pressure at 50, that vapor pressure at 50 would be about 12 kPa. All right, and if it was boiling at 50, then the atmospheric pressure pushing down would also have to be 12 kPa. kPa. All right, so just to give you an idea how things. All right, so really that's about it on how to read the chart. I will fill in the rest of these just so you have the answers. Okay, I got 113 here. You should double check that. I got 90 Celsius here. Please double check that. Okay, I have about 10 kPa here. 10 kPa because it's boiling, they must be equal. Okay, and we got roughly 18 kPa here, 18 kPa here. Okay, and last but not least, I got about 122 Celsius here for the boiling point of ethanoic acid. So that would do it for us on liquids. So have a great day. We'll check you last on solids. Solids will be a really short one, and we'll see you in a little bit.